I will start this third section of the Schlumberger SSA reservoir engineering focus technical session. And the topic of today to share with you will be the continuation of the Petrel Reservoir Engineering Essential Suite and focusing on the geoscreening tool inside Petrel. So with that, I'll move into the next slide to introduce myself. So my name is Henio Alberto, and I am the Reservoir Engineer Technical Consultant for Sub-Saharan Africa. And with me, within this presentation will be also Carlos Romano, which is a reservoir engineer located in Angola, and he'll be also conducting a section of the demo. So welcome to this session, and with that, I'd like to share, myself and Carlos, would like to share you the good things you have with Petrel Geoscreening. So here is the agenda for today's meeting. I will start with a small brief introduction of the Reservoir Engineer Station Suite, and then focusing on the geoscreening itself too. We will understand why is it important. The main challenge that we notice when we do geological modeling that geoscreening allows us to handle. And then we will have a look to the geoscreening workflows. How does it work inside Petrel? We also do a live demo, so you can see hands-on how does the process work. And we will finalize this by showing you the next session and of course, way forward and address your questions. So we have extended the meeting. We expect it to be an hour and a half maximum so that we can allow the demo to go smoothly. If you have any questions, please type it in the message box so that we can answer you and also keep track of the questions and allow to answer everyone's question. Okay. So the Petrel RE Essential Suite, it is a plugin into Petrel. Only requires to be installed one, so it does not come directly with your initial Petrel installer. So it has to be installed separately. But once it installs, so you won't notice as you are using Petrel. And now the different features that are part of the Essential Suite will be part of your Petrel project. It has to be installed in your desktop or in your virtual machine, depending what is your hardware, which hardware you are using. And there is no extra cost associated within this plugin users. License required, so there is no additional cost at all for nothing of what we're showing here to what you already have. If you have the Petrel Reservoir Engineer core or the combined core, so you are entitled to use and to have the Petrel Essential Suite. Okay, and of course we know we also moving to digital, and Delphi is a digital platform, and you can not only using the Petrel Essential Suite on-prem, but you can also capacitate and enhance it with additional 2 digital tools. Now here, I'd like to show you the present day, the items that are composed of the RE Essential Suite. I don't know if you recall from the past session, I showed you 4, which was material balance, geoscreening, the hydraulic fracture modeler, and the EOR screening. And from the last session, the first session, I show you in detail material balance and the EOR workflow. Now, in the new version of Petrel recently released, 2019.4 and 2020, there is a new addition to the Reservoir Engineer Essential Suite, which is the schedule table tool, which allows you to use tables in order to add in and manage complex features using your Eclipse simulator. So we will also prepare another session focused on this so that you can know in detail. Our focus of today will be looking to the geoscreening, which is one of the tools inside of the Reservoir Engineer extension suite. So why do we need screening? And sometimes this is the question we ask ourselves as we are modeling. We know that uncertainty exists, especially when we have lack of data that can reduce uncertainty. When we don't understand some of the main geological features, for example. So this opens ground to the unknown. And screening is what allows us to be able to quantify that unknown. And our uncertainty is spread across different domains, starting from subsurface uncertainty, which is mainly aligned to the geological modeling. How was your model constructed? How sure are you on the channel sands, the thickness of those? How are they interconnected? Uncertainty in the quantification of those parameters. Sometimes we may think that we have a sand channel, which is a very clean sands, very good permeability, good connectivity, but sometimes it's not. There's a mixture of geological bodies such as silt, shales, and a different and multiple geological depositional structures. And this uncertainty will actually impact, number one, our simulation runtime, and of course, our reserves. So it is important that we find a way to address this uncertainty by trying to quantify them. We know by doing that, it requires a lot of time to address all the uncertainties and require models that are very fine and refined in order to address those. And we have to give results in terms of simulation, in terms of reserves to our management very soon. So we need to find a fast way to, number one, account for these uncertainties, but at the same time be able to deliver our simulation results in time. That's why we have the geoscreening tool, which I'll show in detail its functionality. So, as I was saying before, the geological part involves one of the biggest uncertainties we have, and is associated with the full geological modeling, from the structure itself of the reservoir. If it is, for example, a fluvial environment or a deltaic environment which has many channel cross-cuttings, what is the fraction of your channels, orientations, if you have faults, seismic faults or not? How are they located? Are they actually, you have fault transmissibility across all the fault extension? Is it only linked to a specific area of your reservoir where you have channels from one side or of the other side of the fault? If you're doing uncertainty to try to address and quantify these different scenarios that we do not understand, which model is the correct model to use in simulation once the geological model is completed? Are we sure that the model we pick is the best model for simulation and when we do history match? So all of these questions always come and stay in the air as we're doing these workflows, as we are modeling, as we are integrating cross-domain. And I'm going to show you how Geoscreening 2 will allow you to minimize and reduce these questions, these uncertainties, and some of these unknown. And here the question is, which of the models above is the correct one? Imagine you have a green field where you don't have much of production data. We don't know until we produce. If we have a mature field, for example, that we have more production data and we can account and try to understand the reservoir dynamics, still we have to do many tricking as we do in history match together. So the correct model is a process of picking, and I'll show you how Geoscreening 2 can allow us to pick a model that may be representative of the reservoir, volumetrics, and also on the dynamic side. And here is just a simple quotation from Box George, just generally saying that what is the main truth. Essentially, our models are wrong, but some models are useful. And this is the truth. So as we start simulating a field, as we start constructing a model doing the history match until the end of the life of the field, sometimes we state that we only know a reservoir at the end when it's mature enough so that we can predict it. But if we can make our models that we use useful by being able to address these uncertainties, so there will be we can have more confidence in them. And here I have another picture just to show you that sometimes what we think is the reality of the models we are using is not. And we may, in the beginning, thinking that things are going steady and fine, but for example, as we get new data being added to the model or production data coming in, we may start to see that sometimes the smooth of a model can be very wrong when we are predicting some specific dynamic challenge, like water encroachment, pressure maintenance of the reservoir, or for example, new well, infill wells, where can I put a new infill well? So those are things that we want to try to have a more clear understanding, and this is what the Geoscreening tool allows us to do so. So once the geological model is built and is provided to the reservoir engineer, depending on different companies and its internal procedures, could be done using a more simplistic deterministic model, which is the best guess of the geological team in terms of the uncertainties. Sometimes is upscaling in the past, but today we have the simulation capability that allows us to find and run the fine grid models. And also, from this geological deterministic model is the one that will be used for simulation. Another methodology approach from the geological model is they will be run uncertainty through the geological part to be able to quantify what is the P10, P50, and P90 in the STOIP. And the three models will be provided to the reservoir engineer team, which will pick. Probably we'll start with the P50, do some simulations, and then do the same simulation for the P90 and P10, and understand what is the dynamic impact of this uncertainty. But let's say that your model may take a long time to run. And through that, how much realizations you can actually run that are realistic of your model dynamic compared with the history match, for example. Maybe the correct model that match your history is the P47 or the P75. But how do we know this? So geoscreening tool allows us to identify that as well. Now here I have an example just to show you that sometimes when we may pick the model, for example, we have the P10, P50, P90 in STOIP, three models provided by our geologists. And for example, we pick the model P50, we think we should be the most representative. In terms of volumetric, it may be perfect, good. But when it comes to the simulation, is the model that we are finding the lowest production, the lowest rate. Maybe the lower connectivity within our sand channels, our cross channels, for example, are deltatic deposition structures. And maybe it's the P10 model, which may have slightly less in STOIP, but the connectivity of the sands inside that model is better, which gives us maybe a more reasonable production profile. So it is important to associate it, not only the volumetrics, the initial step of the geological model being built, but also its possible production response, because that will give us a more assurance of what is in terms of connectivity of the geological features in the model, the permeability, porosity of this model, and its dynamic response. Is important in an early stage before going to detailed simulation that we're able to understand that I'm receiving a geological model from the geologist, and this model has this probabilistic stope is variation, but at the same time has this specific dynamic response, which is close or far of what I'm seeing in the history match. If that can be done in an early stage, then we start a history match process before we go to the dynamic simulation part. We're doing already in the geological part, take into account the geological uncertainties as well. Now, Geoscreening tool is what will allow us to rank using uncertainty inside Petrel and understand the geological models built, what is its variation in the volumes, but also on its dynamic response. And this dynamic response through geoscreening is done using streamlines. So basically what happened here is that we will be able to assess our models, look into the volume in place, what is your P10, P50, and P90. But at the same time, I'll be able to understand this realization of the geological model, how good is the connected volume from that model. Sometimes we may have a P90 which has lower connectivity, or a P10 which has a higher connectivity. So once we are picking a model to run on the numerical simulator, we need to at least pick a model that is not only probabilistic variation in volume, but also probabilistic variation in the connected part. So this is what geoscreening will allow us to do in a more simplistic way. I'll go in detail. Okay. Now I would like to go on the workflow of the geoscreening process. So it all starts with geological modeling and volume calculation. So this is a workflow that can actually be run by your geologists. They do not need to know a lot of details in the reservoir simulation. They do not need to construct wells and go deep into the connectivity, because to assess the connectivity of the reservoir, we just need to have a flow from one end to the other and see how connected is that flow. So the first part is we need to have the geological model in Petrel and perform a volume calculation to understand what is the volumetric of the static model. The next step is to run a connectivity experiment. This connectivity experiment is done using streamlines, and we will be able to assess the connectivity inside the reservoir. And that this is just one single realization. But if we run multiple realizations using uncertainty and be able to quantify the uncertain parameters we have, both static and dynamic, then we will be able to see which parameters impact both the volume in place and also the connectivity of the reservoir. And finally, let's say you run, for example, 300 uncertainty models in your 300 uncertainty static model, for example. How do you know that the correct model is model number 257 or the realization 152 inside your screen that allows you to pick these models according to their behavior, and then you're able to replicate back uh, this realization with its initial properties, take into account the uncertainty that you have put in to analyze. So this is the workflow using for Geoscreening. I'll go a little bit on detail in each one of them. We start with geological modeling. So there is, you need to have in Petrel a geological model built from the logs, seismic, physics models, petrophysical models, up to the volume calculation. And the reason to this is if you have any uncertainty, for example, in your sand proportion, in, for example, the top of your channels, or in terms of the extension using variograms to your sand bodies, you can use uncertainties to be able to address and quantify those parameters. Okay, so that's why it's crucial you have your geological model built in Petrel, because you'll be able to change those and see both the impact in STOIP and also the impact of your connected volumes. After, once we have the geological model in Petrel, we will run a flow-based connectivity calculation using the static model inputs like porosity, permeability. Petrel will automatically create dummy reservoir properties for you, such as PVT, SCAL, which the purpose is just to assess connectivity. And the good thing of this is you streamlines, you can run very, very fast. So that means it will not consume you a lot of time to filter each realization of your geological uncertainty, what is its dynamic behavior. Then you can pick which wells you want to add in to this flow experiment. You can add existing wells, the wells that you have in your field, for example. If it's a green field, you can use pseudo wells, you can use 5-pot wells, injectors and producers to be able to assess throughout the reservoir, throughout different compartments, different blocks, what is exactly the connectivity you have from one side to the other. Okay, and that can be done simply with this workflow, which will be shown with you in the demo. Now, the good thing of the flow experiment is that the streamlines will actually be able to show you the flow pathway inside your geological realization model. If you have faults, if you have flow across faults, if you have a producer which injectors are supporting this producer, okay, you can check in on tracers. You can check the breakthrough time that will take within an injector in a specific location through the producer. So all these features you can quickly assess in a single simulation run using the connectivity experiment. What is the dynamic of your your single static model realization? Now, let's say that I don't want just to use one unique model. I want to do sensitivity and uncertainty and run many realizations of my static model and see for each one of them what is the dynamic behavior. And through that, we are able to do sensitivity analysis to be able to understand how much my uncertainties I have, both static and dynamic, may impact, number one, the STOIP, which is the fluid in place, and also the connected volume. Some of these uncertain parameters may impact both. Some may impact most the volume. Some may impact most the connectivity. But the good thing is I'm able to understand that in an early stage, and when I'm doing detailed simulation or history match, I know which parameters actually impact those. Okay, so we will be able to rank that through sensitivity, and by doing uncertainty, we're able to go in detail on the on the impact of all of these parameters together and be able to see and pick which realization is my correct or true P50, not only in volume, but also in connected volume inside the reservoir. And I can pick with more confidence a P10, P50, P9 model that is representative of the volume in place and also of the reservoir connectivity. Once that is done, how do I easily recreate that realization that is more, let's say, less uncertain for me? So if you pick one realization, for example, realization 372, how are you able to reconstruct that realization to be able to have the corresponding static model take into account the uncertainties and also be able to pass to your reservoir engineer team? So in the workflow, once we pick one geological realization that we are confident, we can use the reverse workflow to use the combination of the variables that we have used for uncertainty and automatically recreate that to a real static model in Petrel in your project. Okay, and that can then be used for a full simulation purpose. So this is the entire workflow, and if you are in Petrel, having Geoscreening tool, there is a tab that is called Geoscreening, and this is the workflow steps that I just shown you, from the volume calculation, the connectivity, the uncertainty, and the tornado. We will do a demo soon to show you how you walk through, but this is available in Petrel, and through the Geoscreening tab. And if you see, the workflow is basically left to right. So you start by doing the base case connectivity first. If you are happy, then you go to the uncertainty part. After, you go to the model selection. And one thing that I did not mention in detail, but I want to mention now, is being able to do and have a big branch of samples of your geological model and also of your connected within these models. We can do probabilistic maps of the location of your reserves stope inside the reservoir, and also probabilistic maps for your connected volume. With these maps, it's very, very easy to place a well, because through the uncertainty parameters that I have quantified and now I have a better understanding, I can, with more confidence, propose a well location taking into account the remaining reserves, not drain, and also the connectivity, assured connectivity of that reservoir section. So this is also an additional value that Geoscreening can give to you once you complete this workflow, that can help you to reduce the uncertainties when it comes to well placement. So with that, I will stop here, and I'll have Carlos starting the demonstration to show us how does Geoscreening works with flow connectivity. Hello, Carlos. Can you share your screen?
Hello and welcome to the Geoscreening demo. In order to use Geoscreening, you come to the Geoscreening tab and you have these different options: base connectivity, uncertain, model selection, visualization. Volume calculation, we can recalculate the stope if you want, the static model stope, but the actual Geoscreening work starts with connectivity calculation. In the connectivity calculation is where you're going to define how you want your flow-based connectivity calculation. We start by creating new, In the creating new, we then have 4 tabs: model properties, flow setup, expert, and output. We're gonna go tab by tab. In the model properties, we're gonna select the type of grid we want to use. We're gonna select the porosity, the permeability, isotropic or anisotropic if you have it in the different directions, the net to gross, the faults. I'm gonna use faults for this example, horizontal barriers, geobodies, even zones. You can define your flow based calculation based on the different zones you have in the model. If you want to consider also the fluid zones, you can check here and select the contact set that you want to use in your fluid zone calculation. For the example, not considering fluid zones, again go to the next tab, flow setup. In the flow setup, we have 3 different methods: pattern of seeded wells, existing and proposed wells, and edge-to-edge flow. In pattern of seed wells, we can select the type of pattern that you want for the wells, 5-spot, line drive, and so on and so forth. If I select 5-spot, I can select the spacing that I want to use. If I, for example, put 1200, I can check the number of wells that is giving me this spacing. If I, for instance, reduce the number of spacing, I can check again. It's gonna change the number of wells. I can change my method. For example, edge-to-edge flow. I can have flow from left to right. I can have flow from back to front. I can also have flow from top to bottom. And the last method that we have is existing or proposed well, which is going to use the existing or the proposed wells that we have in the model. We start with the producers and the injectors. For the producers, I'm going to use these wells that I have here. Geoscreening producer, I'm going to put all of them. So I'm putting in the folder. I'm gonna do the same for the injectors. I'm adding all of them here, and then we go to the next tab. In the expert tab, we're gonna select the type of flow experiment conditions that we want. We can select to inject 1 pore volume of fluid injected from the reservoir. We can stop the injected when it reaches 0.9% of the fraction of the fluid injected. We're gonna use 1. We can select a pressure difference for forcing flow between the injection and production points. We can select the type of grid that we want. We can even select to show the simulation console or not. And then we go to the output tab. In the output tab, we can select the number of streamlines that we want, the maximum time of flight in days. We can turn this on or off. We can reduce or increase depending on the type of model that you have and computer capabilities. We then do apply, we do run, and when we do run, it's gonna start the running. It's gonna show the simulation console. It's gonna start running and calculating this flow-based connectivity calculation. The run starts and it's gonna show the simulation console. It's gonna run my simulation. It usually doesn't take any time. It is fast. Geoscreening suit. It's very good to understand the connectivity and flow direction in our model before running all these numerical simulations, which take time to build the model, to run simulations. However, with the geoscreening, you can have a quick understanding of the dynamics of our model without having to go all the way to the reservoir engineers to do this type of work. Our G&G guys can do this work and understand the dynamics of it. My simulation is complete. Now I want to see how that looks in our model. We can come here, create a window, put 3D. In our model tab, it's gonna show the streamlines, but I can just quickly click here, show streamlines, and gonna create a 3D window for me with the streamlines here. I can quickly add my wells, and I see the streamlines, its direction. I can see that there is a blank spot here. If I put my faults, if I add all the faults in the model that I have, I see that I don't have flow coming through this fault. However, if I go back here, I can see that there is some flow that goes through this fault. And this is very good to understand the connectivity in our model. But this is just one realization of the flow-based calculation. We can do many realizations. Let me
Mhm.
let me give back to Henio to show the uncertainty and optimization.
Okay. Thank you very much, Carlos. Please let me know if you can see my screen.
Yeah,
Yeah, can you
can
see
see your
it?
screen.
Okay, so follow up on what Carlos has shown. He has shown you only one single model, which we have run using the streamlines. And if I put here, um, and you see the different colors that will come in between the injectors and the producers, is basically the time, and you have the legend here on my left side, that takes to goes from the producer, sorry, from the injector to the producer. And there are zones which takes a long time, and we can see the connectivity between this injector to this producer and how long it takes to connect both. Also, one very good thing, like Carlos was mentioning, is adding the faults, and through the faults, we can see the main boundaries to this flow. But how is this linked to the geological model? And this is what I want to show you. So if I put in here, which is the grid, the fluvial environment, and where we have the channels in purple and the fluvial plain in yellow, we can see across the different vertical realizations that the streamlines will actually follow what is your connectivity in terms of the deposition feature, where you have channels, where you don't have it. If I filter only one section of it, so I'll just come here and put, for example, to be able to show you producer 5. I have here producer 5. I have the connectivity of it, and I only have flow where I have good quality rock type. So the flow that I have ensuring through the streamlines is aligned with the deposition model. And this is just one realization of the model, one single realization. What if my sand thickness is bigger? What if my sand thickness is smaller? What if I don't have much connectivity within the wells across the faults? What if I have a big connectivity between the wells and the faults? So Geoscreening is very nice because it allows us to analyze the connectivity in detail in one unique realization. But we want to understand the impact of the geological uncertainty in those. So in order to do that, what we have to do is using the uncertainty and optimization workflow and be able to model and quantify our uncertainties in a static model. So if you click in that tab, you'll be able to see the uncertainty and optimization process. Here is where we are able to create multiple scenarios, both sensitivity and uncertainty inside Petrel. We will have another detailed section just focused in the uncertainty and optimization workflow later. But here what we are defining is all the steps that we use to create the geological model. And through these steps, we have three main important steps in the geology. One is the phases modeling, the other is petrophysical modeling, where you model porosity and permeability. And I have uncertainty in those. If I do a double click in my phases model, this is where I put what is the fraction of and the size of the channel, how much percentage I have in levees, how much percentage I have in the sand uh, thickness in this case. So I can put this parameter as an uncertainty to me, and I can say for this zone, zone 3 in my reservoir, I have uncertainty in my proportion of sandy and levees, and that will be an uncertain parameter. And you can model all your uncertainty you have in terms of definition of the channel thickness, as the example I'm showing you right now. Also, in the definition of your porosity and permeability, we know porosity and permeability, they vary a lot in the way it is populated. So here you can put variable in the way your permeability is calculated. It is distributed using geostatistical tools. So that means that I will be able to account for the numerical geostatistic errors, or let's say realization impact in how the distribution of these petrophysical parameters will be built. So this is one of my uncertainty, and here to this process I define it. I also have uncertainty in my fault transmissibilities. Are they open? Are they closed? Are they partially sealing? So I'll put also a variable in my fault transmissibility to be able to understand the impact. And now, once I have done this, here are my variables defined with its minimal, maximum, and its distribution. And I will create some scenarios. I'll put 3 scenarios each, so I'll have 18 total runs. I'm just doing sensitivities to understand the impact of each uncertain parameter I have here. So this is done. Once you have complete this, you click apply and run. I will not do it now, just for the purpose of time. I have already done it and run. So what I do, once you finish running, you have a folder in your case panes where you have all the simulation for the sensitivities run. So once you have that, you can come to the next step, which is tornado plot, and you click it to open a tornado plot window, and you are able to display from your sensitive that you have run with the uncertainty parameter you have geologically, what is the impact it has in the STOIP. And here I have my main uncertainties defined. Here are the fault transmissibility. Fault transmissibility has no impact in the STOIP, as we would expect. Permeability has no impact on the STOIP, perfectly, as I would expect. And then the fractions of the sand, the proportion of the sand, the levees, the porosity, has a big impact in the STOIP. But my question will come, how does these variables also impact in the connectivity of these cases? So I'll do here another plot, and I'll put them side by side so that we can see it, where I wanted to visualize what is the impact of these variables into the connected volume. Okay. Okay. So on this plot here, I can see here is the total cumulative flow production. And I can see that now, for these sensitivities I have done, the fault transmissibility has an impact in the connected volume. This is the total connected production volume. And here you see the fault transmissibility has a big impact in the connectivity, and of course has no impact in the STOIP. The permeability has an impact in the connectivity, but of course has no impact on the STOIP. So I can use a tornado plot to be able to visualize each one of these uncertain parameters, how they impact both the STOIP and also the connection volume inside the reservoir. Okay, and we can see here the big contributor to the impact of the STOIP, T-Frac1, is the second one contributor to the connected volume. So I can see a direct link of the proportion of the sand both to the volume in place and also to the connection volume in place. Sometimes when we do in history match, what we do, we use permeability multipliers, we use pore volume multipliers because we want to get that flow to match the pressure and we want to get that production. Where what we actually have to move to change is the proportion of a sand. And this will give you directly the flow that you need. So those are important parameters that Geoscreening allows us to filter out and be able to understand before we go to full detail simulation, the contribution and the part of geological parameters in your flow connectivity. Now, since we have done this, and this is just sensitivity to see each parameter alone, how does it impact, let's run uncertainty to be able to combine all of them together and run more realization. So you go back just to check, can you hear me well? Can you follow? Can you see my screen?
Yes.
Yes.
Okay, thank you. So I'll go back to the uncertainty and optimization tool, and I will create a new workflow, which is basically come here and change to uncertainty, okay? And I'll put what parameter I want, Monte Carlo, and the number of realizations I want to run. I have here one already done for the purpose of time. So I'm creating 250 realizations of both static and dynamic model. And a question that may come is, how do you integrate both the static and the dynamic model? And it's out here in this workflow. I show you the workflow to add in the geological uncertainties. You do the volume calculation, and one only difference from the normal geological workflow uncertainty is that you add here the geoscreening flow connectivity to as part of your simulation. That means every single realization that we create, he will create one unique static model and one unique flow corresponding of this static model. The workflow is exactly the same. If I click here, you'll be able to open the flow experiment. Same thing as Carlo has shown you before. And you run the simulation case using that flow experiment. So it's exactly this. And I have run the uncertainty with 250 cases. So that means he will create 250 unique static models using this combination. And he will create also 250 unique flow connectivities associated with the static model. Okay? So once that is set, I click apply and run. For the purpose of time, I have done that already. And you have here on the case pane, you have a folder with my uncertainty, and you have all the cases that I have created. I'll just put here so you can see. So you have all the scenarios created. For each realization of the volume calculation, it will create the same for your connected flow. Okay? But the question is, how are you able to digest and understand how they interact with each other? And this is what I'll show you in the next step. So what you do now, following the geoscreening workflow, you go into the master table, and within the master table, you add in all your simulation that you have created, both for the flow experiment and also for the volume in place. Here I have one already done. I'll just quickly delete and show you directly how you can do it. So basically what you have to do is come here to your uncertainty scenarios. For the volumetrics, you add here This is your static model. You can select all of it, and then you can add them so that you can add in the entire volume calculation for this table. I'll select it here. I'll select here. So this is if you're doing for one case, but if you're doing for all of them, you select each one and you add. You not to be doing this one by one. This is just to show you that there has to be a link between the corresponding volumetrics model with the corresponding with the corresponding flow dynamics. Okay. So from that, once that is done, you can add them automatically by selecting the folder and adding dynamic and static. You add in the entire set of the flow experiment, the entire set of the volumetrics, and then on the parameters, we're able to select which uncertainty variables you want to see. Remember, those are the same uncertainty variables you saw in the tornado that we created in the workflow, and you can select which one you want to add in to additional detail analysis. Okay, so these are the cases parameters. For the volumetric calculation, you want to choose which parameter you want to select. I will pick STOIP. For the streamline calculation, it will give us vectors, which is the same of your production vectors. And here we have the connected per volume, the connected fluid production, injection volume for all the cases. I will add on. And on the flow calculation tab, you want to see what you want to calculate. I want to see my connect fluid production cumulative. So you add in all this, you just have to select which ones you want to visualize. And after that, you click apply and OK. All right. So this will create a geoscreening master table in your input pane. If you go to your input pane, I will collapse mine, and you have a folder which is your geoscreening master table. Okay. Once that is done, I come here to my case selection. I select the master table that I have, which is the master table 1, and I'm able to start to analyze this cluster of data. So it's a lot of simulation points from the connectivity to 150, and there's a lot of volume calculation. How do I quickly filter out? How do I pick a case? It's all done using this make case selection tab. So in here, I can say I want to see 1D cluster, just one property, and I want to see what is my distribution of my photomultiplier. My photomultiplier varies from 0 to 1, and the cases are quite linear. Okay, very good. I want to see what is the distribution of my STOIP. I'll come here, I'll click STOIP, and from the 250 realizations, I have here the distribution and also the cumulative distribution function. All these points you are seeing here in green, blue, and red are the simulation cases that fit into those distribution trends. And you can change the percentage you want to have to increase the range of this parameter. Okay, so for example, you can put 8 or 10 for your P50. Okay, and what you do, it will increase and show you more cases which are associated with your case P50 inside here. Okay, the other thing you can do is, I'm only looking STOIP. I see the cases of P10, P50, P90 STOIP. How do these models behave in terms of connectivity? Now I'll go to the second 2D and I'll select my variables. These are both the static and the dynamic variables. And I can put here my connect fluid production, and I have this cross plot, the same one as I shown you before, which will plot the STOIP, the connected volume, and how the realizations I run, how do they plot here. You can see the growing up trend, and the cases that are inside my range, so this is 90%, sorry, this is exactly the 90% range in terms of STOIP, and also the 90% range in terms of connectivity. And the models that are inside this range are the ones that are showing with these red dots. Same thing with the blue dots. You can see it's a very small window here, very small window of P50, and a much wider window of P10. And I can select the models. There is one selected here. I'll select this model here. I'll select this model. So I selected 3 models for my P90. I selected, for example, 2 models for my P10. 3 models for my P10. Okay. Once I have selected these models, I go to the next tab, which is case selected. It will show me all the cases inside the range, and I will filter just to see the one I pick. So those are the models realizations I pick. These are the STOIP, they connect the volume, and for example, I can add more tabs. I can say, I want to see exactly what is this case, what is the name of this case, so that I know where to get it. And I can go and select case name, for example, here. And I'll have another tab that will show me exactly which realization is giving me the P50 in STOIP and P50 in connected volume. Okay, so these clusters allow me to select cases, allow me to filter cases. But now you can tell me, look, you have here a model which is P50 in STOIP, but P90 in connected volume. And I'm pretty sure that the model I have, my project, this is the volume in place. I don't expect to be more. But the production associated with this volume is higher. So if this is your case, if you have production data and you can double check that, this is a realization of your model that will give you that response. You have the same STOIP in place, but you have more connected volume. That means you can produce more, the sands are more interconnected, interlinked, and you can have a higher production. So using geoscreening, you can pick geological realizations that can allow you to address some history match challenge we have in terms of in-place volume, in terms of connectivity. Sometimes we say we have big problems assessing connectivity. Our model is not very connected. I have to increase the permeability times 3, times 4. Sometimes we don't need to increase the permeability. The permeability is correct. What is not correct is how the porosity has been distributed, how the sand proportion has been modeled, and this realization of your geological model may do that. Okay, so from here you can select each case is suitable for you. Each case represents the dynamic, P50, P90, both in STOIP and in connected volume. And through that, you know the cases that you have here associated, and you can go directly and pick that realization of your model. For example, you can pick case 271, the weak read, okay? One other thing is you can really go to much detail analysis. You can compare different clusters from the certain parameters that you have. For example, you may want to see how does your connected production is varying with your fault transmissibility. So if I come here and put fault transmissibility, I can see I don't have a much clear trend. There's no a much direct relation within these two properties, linear relation, okay? So you can really play around all the clusters and understand the interaction between those and pick a model that is representative of that scenario. Okay, so this is what this master table will allow you to do. And once you have picked one case and you have seen I'll pick case 271, so you can come here to your geological, to your uncertainty and optimization tool and select case 271, right click and recreate workflow. What it will do, it will get all the uncertain parameters values that was used to build this realization that give me a good trend of stope and connectivity, and will automatically recreate the geological model grid in order for you to have it. Okay, I will I will um, I will just apply and run this one just to see if this is okay. And you can have a complete new grid extracted from this uncertainty realization that will be able to address you and give you the main response for both static and dynamic behavior. Going back to my models, and from my models, I have here the new grid with that specific behavior, which you can then use for simulation. One other good thing that that you can do, as I was mentioning, was uncertainty maps. So once you have done and run all these clusters, and you have 250 unique static models and each flow behavior, I can create probabilistic maps. Probabilistic maps using, for example, I want to see the mean or the standard deviation or the variance, depending on what you want to choose. For example, I'll choose mean. I'll select in the master table, which is all those cases I have run, and I have to add in a surface so that I can create a map. And through that, I click apply, and it will use the compilation of all this information, the volumetrics and the connected volume, in order to give me a probabilistic map of what is the zones that have a higher probability to have oil in place, the zones that showing the higher connected per volume, and the zones that are showing the highest connect volume production. It's just calculating. Just give a minute. But this tool is very useful because after done this exercise, especially if you look into green fields, take into account the uncertainties that you have quantified them, and also a possible dynamic behavior, you can now I'm just expanding this map so you can better see it. I'll fit into the screen, and I'll come here and I will select what I want. So I'll come here to the net. Okay. I'll just do a zoom out. And what I do, I will use a color legend just to be able to see it. Okay, so here through this map, I can see the areas that have higher probability of connected portfolio. Let me add in my wells. So I just quickly add in my wells, injectors, and producers. So here are my wells, and in terms of zones of we're showing higher permeability of connected pore volume, I can see, for example, where I can add in additional well, infill wells, for example, beyond the ones that are there already. Okay, I can see, for example, the connect fluid production the zones that I have higher probability of producing the most. If I want to add a new infill well, why not add here, take into account all this probabilistic study that I have done. Okay. Connect the portfolio. So all these tools are here, available for you to be able to see what is the main response of your field. Okay, so all of this is possible because you're able to take into account the uncertainty that you have static, and you're able to simulate it using streamlines and see what is the expected dynamic behavior of those. If I open now a 3D window and I'm finishing, I just want quickly so that you can see, I can visualize it, all the cases that I have run. So they all will be here, the same way you use Eclipse or the same way you use Intercept. You can select field and you can quickly see what is your connect fluid production cumulative. So this will give you realizations of models that you can very quickly produce the reservoir volume, and models that will take you longer to produce the reservoir model. And all of those have different connectivity within them. Okay? And you can see which realization will give which type of behavior of your model. So this is the base for fully automate and artificial learning history match. Because now the workflow will be not vary individual parameters, is using these parameters as uncertainty and optimization and pick the model that will give you the response that match your history. And Geoscreening allow you to do that. Here, for example, I can put production. I can see models that can give me higher production and models that can give lower production. Okay, so with that, I will finish this presentation and demo, and I'm happy to take your questions if you have a question. I know there are questions in the chat window. If not answered, I can answer them, or if not, you can raise your hand, and I'll be happy to answer your questions. Thank you. Some questions I see already that have been answered by some of the team. So while we wait, Juan, please, can you unmute and let me know your question?
Maybe this question was addressed during the presentation, but I didn't catch the subject. You briefly mentioned it. Is this workflow, where is the history matching sitting? Is this pre-history matching, post-history matching, or without history matching?
Well, to be honest, I'll say that you can use at each one of these steps. It would be, for example, if you have a green field that you don't have much production in order to simulate it, and you are receiving geological models from the G&G team, you may want to request the models that will give you not only a variation in STOIP, P10, P50, P90, but also in terms of its connected volume. So that is, for example, in a scenario that is a prehistory match, okay? So that you can do field developments, but take into account that that model has not only that volume in place, but also that put through in terms of connected, in terms of dynamic connectivity. Now, let's say you have a field that is producing for a couple years, or for example, a brown field, and you may have a lot of challenge because you are facing challenge in connectivity within different sand values, for example, or let's say injector to producer, cycling of your injected volume, pressure maintenance. So fields that you have these challenges, and you want to try to match your data, or let's say fine-tune your model with this dynamic behavior, then you can use geoscreening at this stage to help you pick realizations that will give you this behavior automatically from geological model, rather than you trying changing parameter by parameter in time. So you can use in both, depend on each stage you are. If you are if you are in a stage of a greenfield or in a brownfield, for example, it can be applied to each one of these phases. Also take into account that you also have uh, good probability of proposing fuels take into account its dynamic behavior. So you can do that in the early stage or with the remaining saturation in the later stage, if you're able to account for the zones that are undrained in your reservoir.
So in the case of where you already have history, you constrained the number of static realization that you can have.
Yes, so if you have history, so you can exactly constrain the number of realizations. For example, you may not want to do many, but the number of realization is mainly how much realizations you need to account for the uncertainties that you have. You want to have a smooth cumulative distribution function so that you really can see with clarity your P10, P50, P90
Yes.
in the
You,
accepted
you,
parameters.
you are correct. You
So
are correct. What I mean
so
is
you
that the
can
number of parameters that you should change. Is that you are
yes you have less parameters indeed you have less parameters because you probably have less uncertainties taken into account some of the so yes. But
exactly?
one
Thank you very
thing
much.
is, for example, you have a producing field where connectivity is a challenge. We know in West Africa and East Africa, within the multiple turbidite reservoirs that we model, and which have cross-channel uh, um, 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 connectivity, you can still use it, your screen, to help you model the channel thickness, okay, and also your connected flow between injector producer or aquifer to your producer, able to model in terms of breakthrough time and also which area is getting support. So Geoscreening will also help you to pick the realization that show you that.
Thank you.
Yeah. Carlos, do you have any question?
Yeah,
In
we
the
have we have two questions that has not been answered. One is from Esperanza Francisco. It says, to generate streamline, is it mandatory to use conceptual producer injector pairs, or we can on streamlines convergence to producers from reservoir expand boundary?
I'm sorry, Carlos, can you please repeat the last part?
Or we can on streamlines converging to producers from reservoir expand boundary.
Okay, yes.
I
So,
think
yes, it was answered, but
yeah, it
I
was
will quickly
answered.
address again. So you have three ways. You can use pattern wells, which is a combination of producers and injectors in a pattern. You can use your existing wells that you have now in your field to understand how do they interact, how well do they drain your reservoir, not which areas you have unsweep or not sweep, the connectivity within them according to your geological feature, or you can use edge like you show in the demo, edge flow from the south or from the north. Normally to try to mimic if you have a strong aquifer that is pushing oil, how is that flow, that pathway going? So you can use those three options as a scenario. I see a question from Nelson.
Yeah,
You
there
have
is
your
one.
hand, please.
Yeah.
Yes, Carlos, please.
Yeah. It says, since the streamline and connectivity are dependent on the static model property distribution, which in itself may not be correct, will it not be risky to rely on the geoscreening results in planning wells?
Um, Actually, this is why we use geoscreening, because I won't say it is your unique tool to make a decision. You can have many, but what geoscreening will allow you is to use multiple realizations of your static model to be able to compute a probabilistic map, as I show you, take into account the area that you have uh, a higher accumulation of volume and connected volume. So actually, geoscreening will reinforce or will help you validate it in free well zones, because it will not show you zones that have higher probability of have accumulate reserve, but if those reserves can be produced in terms of connectivity with other areas of your reservoir. And if there is no well that can drain those areas, you can add in infill wells to it. So actually, through geoscreening and with the help with the uncertainty that is inside geoscreening and the multiple cluster analysis that you can choose to pick models that can help you answer those questions. Remember that all those models in the cluster are unique probable realizations. So use the same input, vary your parameters, so they are equiprobable. That realization of the model, one unique realization of your model will not give you higher confidence, but if you use uncertainty through the geoscreening through running many parameters in order to account for uncertainties that you have more confidence proposing a well. Take into account two things: reserves in place and connectivity to be able to drain those reserves in place.
Henio, thanks. Hello?
Yes, please. Hello.
Yeah,
Yes. No.
yeah, thank you. But what I'm saying is, I think for a brownfield where you have history or production data to actually, to some extent, validate your model, it makes sense because you are working towards, you already have an answer. Answer is okay. What is the observed that you have, the production data and all that. So you are working towards, what is the subsurface, structure and everything and all the properties that will give you that answer that you have already have, which is the observed. But for like a greenfield, where we don't have anything to validate it, will it not amount to, just generating different kind of models that all through the model you are not even sure if any of the model is correct, because the model that gives you the highest production might not be correct. It can give you the highest
Exactly.
production, fine, but it might not. It doesn't mean that that model is correct. You understand?
Mm-hmm.
The model that
Yes.
says a fault is connected, it might not be correct because the fault in actual fact might not be connected, but it's saying that it's connected and it's giving you high production. So that's why I was asking the question.
Mm-hmm. Yes,
And
and thank you, Nelson. That is actually a very good point. One thing I would say is for greenfields, especially when you don't know, what your skin allow you to do is for you to pick models that with more confidence. You may say, well, I want to pick a model that have higher STOIP and higher connectivity. You don't know. Maybe it's the model with low STOIP and lower connectivity. But you know, especially in the greenfield, as you are selecting this case, you have more certainty of what kind of models you want to pick. And that will come in with your understanding at the time of the reservoir possible behavior. Take into account your geological description. If you know the faults, many faults, but some of them may be sealing, maybe you want to pick a model that is not giving a higher, let's say, a big connectivity. So in a greenfield, it is a little bit of there still be uncertainty, of course, until you produce, you get data and you can match it, but you'll be able to pick realizations more consciously rather than just picking P10, P50, P90 in stop alone and not know the possible dynamic of those fields. So that will give you just, I think, more confidence in the model you select going forward for your analysis, and you know uh, um, which uncertainties you are taking with that model.
Okay.
You know that, and that will
Okay.
give you more confidence as you go forward.
Henio, can I add to that? This is Sam.
Yes, please.
Okay, so Nelson, I guess I believe that that's a very good question that you've asked. But if you remember one of the slides presented by Henio, whereby if you select your P50, P90, P10 on the basis of the static response alone, like STOIP,
Yeah.
you might miss some surprises whereby when you get to the production, they might not actually exactly this slide, they might not deliver the same consistent dynamic response with your STOIP.
And such module is actually completely wrong because it doesn't make sense. Because something that shows in terms of the volume before, and you take it as your P10, but when it comes to, you think this is my P10, but when you now see recovery, it turns out to be P50. So there is inconsistency. So even though we don't know at the greenfield because there is no production to constrain those selection of those modules, but it gives you the benefit to select modules that are consistent throughout. And that is the first benefit. Remember that, like he also said, that all modules are wrong, but some are useful at the end of the day. So you want to select something that is not just mathematically correct, because all the realizations are mathematically correct, but they are not all geologically realistic.
Correct.
So what you are trying to do is to select consistent module at the beginning until you have production to actually constrain those cases and select a better one, because production will give you more understanding of the field. And that is what we're doing at the green phase at the early stage.
Okay. Thank you very much.
You're welcome.
Thank you, Henio.
Thank you. Do we have more questions in the line? If you have a question, please, you can unmute yourself. Yes, please.
I think there's also a question. Sorry, okay, Kabiru, you can go ahead before this one.
Okay, Thank you, Henio, for that presentation. What I want to find out, the geoscreening tool, how different is it from surrogate modeling using experimental design and the same, the Petrel package? How different is it?
Well, I think that the big difference in terms of the geoscreening tools is like it will combine and will be able to allow you in a quick way to address the multiple realizations and its dynamical behavior. Okay, so for some other modeling, you have one initial static or parameters defined, and you quickly run it to see its dynamic response. But as I was mentioning before, the good thing that Geoscreening allows you not only through the flow connectivity experiment, see the flow lines and understanding where are you connecting jet producers, support connectivity, but allows you to add in the uncertainty over it, allows you to be able to select multiple realizations, take into account those two parameters, static volume and connected volume in place. And for example, allow you to have also the mapping part, which is take into account all those clusters and you're able to play the mapping. So those are a lot of additional things you can add in from Geoscreening alone. Now, the other part is some of the normal analytical simple surrogate models. We only help you, they are quick. So you can run it, fine, you can see from this model, my expected production is X. But you won't have the flexibility to go to your geological model with geological understanding, change your geological understanding. And it may take a lot of time to set those. While geoscreening, it quickly creates dummy parameters, dummy PVT, dummy ROPERM, because that actually does not impact the connectivity. You just want to assess the connectivity. So quickly create those parameters and allow you to simulate faster. One other thing, easy way for you to compute wells, easy way for you to define source in sync, edge view. So all those things actually separate geoscreening from this other type of modeling. And being integrated from Petrel even makes it easier through that. So I'll say just highlight on the geoscreening part the benefits, which makes the difference.
Yeah,
I'm not sure if I answer your question.
Kabiru.
Kabiru.
Hello.
Yes.
Yes.
Kabiru, maybe I should just. Okay. I was thinking of just making some addition to that. So if you look at Petrel experimental design that we use, so it enables us to select the algorithm to run certain scenarios. For example, if you're using like Monte Carlo, for example, or you're using Block-Obermann, it allows us to run different experiments, like different cases. So which we can do in dynamic or we can do in static. So these are independent, done separately. So if you look at the slide that Henry presented, he mentioned he did a case where we looked at uncertainty analysis using Monte Carlo. So that is under static, for example, in one scenario. So what Geoscreening would do for you is to bring in both static and dynamic in one place. So that is what it does for you. So if you run Monte Carlo or run any experimental design independently, you can do that in Petrel independently in static, or you can do that in dynamic. But then we can bring that in one place, like using example of let's say Monte Carlo as a typical example, or using plug and Brahman or whatever it is. You can bring that in one place. So that is just the difference here. So you can apply them and then in geoscreening, but then you're bringing them in one single place. So I hope that answers your question.
There is also one quick thing I can add in. Has also is something you can use geoscreening for. Is imagine that you have already done uncertainties studies
Yeah,
using
okay, that's
eclipse
fine. I was
or
just
intersect.
thinking that if the entire project, hello?
Hello? Yes. So, for example, just to show you one example, if you, here we use flow experiments, but let me say that you have already done multiple uncertainty study using eclipse or intersect. Through the geoscreening master table 2, you can actually, on the flow experiment, you can add in your correspondent eclipse or intersect model. So you can add also your numerical simulator if you have done this analysis, and use the geoscreening cluster to also be able to select those cases. So this is one additional feature that I can mention that you can use geoscreening for.
And what I can add to that, in terms of the surrogate module, we need to also think about the application. So the application of the surrogate module, you have to select them carefully. If you are doing uncertainty propagation, that is fine. You can use surrogate module once you train the proxy very well. Then you can populate as many as you want to populate on the basis of that proxy algorithm to populate the your realizations. But this is actually doing a very more detailed work in the selection of the module. And it's seeing those modules actually to understand the connectivity, because it's like you're running a flow simulation module, not just using analytical equation to predict that has been trained. Hello?
Hello?
Yeah. So Kabir, Abi, is that okay on your question? Okay, maybe.
Yeah, I think it is. Do we have more questions?
So I think there's a question. Somebody's asking if we have that if they have Petrel RE license, if they can do geoscreening without having a separate license.
Yes. So
I think
if
that's
you have
coming
Petrel,
from Equan. Equan is asking that question.
Okay. Ikon, thank you very much. So if you have a Petrel RE license, so and you don't have geoscreening already active, please just contact us through me, myself, Samuel, Limi, or your account manager, and we'll provide all the required setup. What is the setup? We have to provide you the plugin so you can install, and you have to provide you the correspondent license. As I said before, there is no additional costs related to this. It's just the setup that has to be defined. Okay, so you can do that. You can use it. And there is two different licenses, one for Petrel and one for geoscreening, which is part of Petrel's Tensor Suite, but there is no cost associated. So if you don't have in your machine active, just let us know and we'll provide that to you.
Okay, I guess we can end now.
Okay. So with that, I would like to thank everyone for attending this session. And our next session will be in a week on Depot Grid. And I also I want to mention that this tool is available today, so you can use it, you can explore. You have the capability to go in detail in your analysis, in your field, in your model, so do so. If you have any questions related to it, or if you want to go in more detail, please let us know. We're still working on the recording of the session. We're trying to find the best way to share with everyone, also taking into account workflow. So once that is sorted, we'll put not only out the previous and this one, out the recording links available to you. And I can say in my name and Carlos and the entire team, thank you for having us, and we count on you next week.